Hello, welcome to the video lecture series on digital image processing. Now, there are other approaches of degradation mathematical model for to estimate the degradation, which are obtained by fundamental principles. So, from the basic principles also we can obtain what should be the degradation function. So, one such case, so here we will discuss the basic principles, the degradation model estimation from basic principles. And I try to find out what will be the degradation model, degradation function, where the image is degraded by linear motion. And this is a very common situation, that if we try to estimate or if we try to image a fast moving object, in many cases we find that the image that we get is degraded. There is some sort of blurring which is known as motion blurring. And this motion blurring occurs due to the fact that whenever we take the snap of the scene, the shutter of the camera is open for certain duration of time. And during this period, during which the shutter is open, the object is not stationary, the object is moving. So, considering any particular point in the imaging plane, here the light which arrives from the scene does not come from a single point, but the light you get at a particular point on the imaging sensor is the aggregation of the reflected light from various points in the scene. So, that tells us that what should be the basic approach to model, to estimate the degradation model in case of motion of the scene with respect to the camera. So, that is what we are trying to estimate here. So, here we assume that the image f x y, this undergoes motion, and when f x y undergoes motion, then there will be some moving component. So, I assume two components x naught t and y naught t, which are the moving components or time varying components. So, these are the time varying components along x direction and y direction respectively. So, once the object is moving, then the intensity, the total exposure at any point in the imaging plane can be obtained by aggregation operation or integration operation, where the integration has to be done over the period during which the shutter remains open. So, if I assume the shutter remains open for a time duration given by capital T, in that case the total exposure at any point, which is the observation at point x y given by g x y, will be of this form: f x minus x naught t, y minus y naught t dt, and integration of this from 0 to capital T. So, here the capital T is the duration of time during which the shutter of the camera remains on, and x naught t and y naught t, these two terms, they are the time varying components along x direction and y direction respectively, and this g x y gives us the observed blurred image. Now, from this we have to estimate what is the degradation function or the blurring function. So, once we get g x y, then our purpose is to get the Fourier transform of this. That means, we are interested in the Fourier transformation g u v of g x y, and this g u v, as we know from the Fourier transformation equations, is given by g x y into e to the power minus j 2 pi u x plus v y dx dy and take the integration, double integration from minus infinity to infinity over both x and y. So, it is this expression, using this Fourier transformation expression, we can find out what will be GUV, that is Fourier transformation of the degraded image GXY. And if I derive this, it will be of this form. So, minus infinity to infinity, again minus infinity to infinity. Now, this GXY is to be replaced by 0 to t, the expression that we have got earlier, f x minus x naught t, y minus y naught t dt into e to the power minus j 2 pi u x plus v y into dx dy. So, if we just do some reorganization of this particular integral equation, we can write G u v in the form G u v equal to integral 0 to t double integral minus infinity to infinity minus infinity to infinity f x minus x naught t y minus y naught t dx dy into dt. Now, from this particular expression, you find that the expression within this bracket, sorry, there will be some more addition. So, the final expression will be like this. G u v will be equal to 0 to capital T, then within bracket we have to have this double integral varying from minus infinity to infinity f x minus x naught t y minus y naught t e to the power minus j 2 pi u x plus v y dt and then dx dy and then dt. So, this will be the final expression. Now, in this, if you look at this inner part, this is nothing but the Fourier transformation of shifted f x y, where the shift in the x direction is by x naught t and shift in the y direction is by y naught t. And from the properties of Fourier transformation, we know that the Fourier transformation is shift invariant in the sense that the Fourier transform magnitude will remain the same, only it will introduce some phase term. So, by doing that, we can say that this f x minus x naught t y minus y naught t, this will have a Fourier transformation which is nothing but f u v e to the power minus j 2 pi into u x naught t plus v y naught t. So, this is from the translation invariant property of the Fourier transformation. So, using this expression, now the expression for g u v can be written as g u v will be equal to integral 0 to capital T f u v e to the power minus j 2 pi u x naught t plus v y naught t dt. And because this term f u v is independent of t, so you can take this term f u v outside the integration. So, the final expression that we get is f u v into integral 0 to capital T e to the power minus j pi j 2 pi u x naught t plus v y naught t dt. So, from this you find that now if I define my degradation function h u v to be this particular integration. So, if I define h u v to be this, then I get expression for g u v is equal to h u v into f u v. So, here this motion term, the degradation function is given by integration of this particular expression, and in this expression this x naught t and y naught t, they are the motion variables which are known. So, if the motion variables are known, then using those motion variables, the values of the motion variables, I can find out what will be the degradation function, and using that degradation function I can go for the degradation model. So, I know h u v, I know g u v, and from that I can find out the restored image f u v. Now, in this particular case, if I assume that x naught t is equal to a t upon t and similarly y naught t, I assume this also to be some constant b t upon capital T. That means, over a period of capital T during which the camera shutter is open, in the x direction the movement is by an amount a, and in the y direction the movement is by an amount b. So, by assuming this, we can find that h u v by using that integration, by computing that integration, will be given by 1 upon pi u a plus v b into sin pi u a plus v b into e to the power minus j pi into u a plus v b. So, this is what is the degradation function or the blurring function. So, now let us see that using this degradation function, what is the kind of degradation that is actually obtained. So, here again on the left hand side we have an original image, and on the right hand side this is the corresponding blurred image, where the blurring is introduced assuming uniform linear motion. And for obtaining this particular blurring, here we have assumed a is equal to 0.1 and b also equal to 0.1. So, using these values of a and b, we have obtained this we have obtained a blurring function or degradation function, and using this degradation function we have obtained this type of degraded model. And you find that this is quite a common scene, whenever you take the image of a very fast moving object, the kind of degradation that you obtain in the image is similar to this. Now, the problem is we have obtained a degradation function. Now, once I obtain a degradation function or an estimated degradation function, now given a blurred image, how to restore the original image or how to recover the original image. So, as we have mentioned that there are different types of filtering techniques for obtaining or for restoring the original image from a degraded image. The simplest kind of filtering technique is what is known as inverse filtering. Now, the concept of inverse filtering is very simple. Our expression is that G u v, that is the Fourier transform of the degraded image, is given by H u v into F u v, where H u v is the degradation function in the frequency domain and F u v is the Fourier transform of the original image, G u v is the Fourier transform of the degraded image. Now, because this H u v into F u v, this is a point by point multiplication, that is for every value of u and v, the corresponding f component and the corresponding h component will be multiplied together to give you the final matrix, which is again in the frequency domain. Now, from this expression, it is quite obvious that I can have f u v, which is given by G u v upon H u v. So, where this H u v is our degradation function in the frequency domain and G u v I can always compute by taking the Fourier transformation of the degraded image that is obtained. So, if I divide the Fourier transformation of the degraded image by the degradation function in frequency domain, what I get is the Fourier transformation of the original image. And as I said that when I compute this H u v, this is just an estimated H u v, it will never be exact. So, the reconstruction of the recovered image that we get is not the actual image, but it is an approximate image, approximate original image, which we represent by H u v f hat u v. Now, here as we have already said that G u v, if I consider the noise term, is given by H u v into F u v plus the noise term N u v. Now, from here if I compute the Fourier transform of the reconstructed image, that will be f hat u v, which is equal to G u v upon H u v, and from this expression this is nothing but f u v plus N u v upon H u v. So, this expression says that even if H u v is known exactly, the perfect reconstruction may not be possible, because we have seen earlier that in most of the cases the Fourier transformation coefficients are very, very small when the value of u and v is very large. So, that means for those cases N u v by H u v, this term will be very high, that means the reconstructed image will be dominated by noise, and that is what is obtained practically also. So, to avoid this problem, what we have to do is, for reconstruction purpose, instead of considering the entire frequency plane, we have to restrict our reconstruction to a component of the frequencies in the frequency plane which are nearer to 0. Since if I do that kind of reconstruction, that limited reconstruction, in that case the dominance of noise can be avoided. So, now let us see that what kind of result we can obtain using this inverse filtering. So, this shows an inverse filtering result. Here we have the original image, in the middle we have the degraded image. So, this degraded image we had already shown. So, this is the degraded image, and you find that on the right hand side this is a reconstructed image using the inverse filtering, when for reconstruction all the frequency coefficients are considered. And as we have said that as you go away from 0 0 component in the frequency domain, that is as you go away from the origin, HUV term becomes very negligible. So, it is the noise term which tends to dominate. So, you find that in this reconstructed image nothing is available. Whereas, if we go for restricted reconstruction, that is we consider only few frequency components near the origin, as has been shown here, that we have considered only those frequency terms within a radius of 10 from the origin. So, this is the reconstructed image, and as it is obvious, because our domain of reconstruction, the frequency components that we have considered as very limited. So, the image becomes reconstructed image becomes very blurred, and that is the property of the low pass transform. This is nothing but a low pass filter, and that is the property of low pass filter. If the cutoff frequency is very low, then the reconstructed image has to be very blurred. In the middle of the bottom row, again we have shown the reconstructed image, but in this case we have increased the cutoff frequency. The cutoff frequency, instead of using 10, now we have used cutoff frequency equal to 40. And here you find that if you compare the original image with this reconstructed image, you find that the reconstruction is quite accurate. If I increase the cutoff frequency further, as we said that it is the noise term which is going to dominate. So, on the rightmost, here we have increased the cutoff frequency to 40. So, here you find that we can observe the reconstructed image, but as if the objects are behind a curtain of noise. That means, it is the noise term which is going to dominate as we increase the cutoff frequency of the filter. So, with this we complete our today's discussion. Now, let us come to the questions on today's lecture. So, the first one is, what is point spread function? The second one is, how can you estimate the point spread function of an imaging system? Third question, which degradation function can model atmospheric turbulence? And the fourth question, what problem is faced applying inverse filtering method to restore an image degraded by uniform motion? Thank you.